All right, we're going to take the function ln of x minus 1. We're going to create a polynomial centered around the number 2 that most closely represents that logarithm. Because we'd much rather plug something into a polynomial than we would a logarithm, especially if we're doing it by hand. All right? So before you do that, you're going to need the derivatives, just like we had with linearization. So let's kind of go off to the side here. And if we know that f of x is the ln of x minus 1. All right, Juliet, oh no, you've done a couple. Alex, give me f prime. Okay, all right. Kaylin, give me f double prime.
Negative x to negative 2.
Close. Let's remember that this is x minus 1 to the negative 1 and treat it like a quantity. Okay, make sure you treat it like a quantity.
Negative x to the 1 to negative 2. X minus 1 to negative 2.
Okay, so negative x minus 1 to the negative. So I'm going to say negative 1 over quantity x minus 1 squared. And then we're going to need the third one. All right, so Edson, that one.
2 over x minus 1 to the third.
Okay, so we're going to need those three derivatives because we are going to create a linear, which takes derivative 1, to quadratic, which takes derivative 2, and we're going to need the third derivative, which is going to, the cubic, which is going to take derivative 3. All right, now we're going to find the values at 2. So we need to know from all of these what f of 2 is, what f prime at 2 is, what f double prime at 2 is, and what f triple prime is. All right, so do the one you did the derivative of. Okay, so Edson, if you could do the triple prime value. Kaylin, if you could do the double prime value. Christian, can you do single prime? And let's see, who can? Alex, can you do the f of 2? Okay. All right, f of 2 is ln1, and what's ln1?
0.
Okay, thanks. All right, Christian?
1.
Okay, thanks, Kaylin.
Negative 1.
Okay,
2.
all right. Okay, so we've got those, and we talked last week about how to build a linearization. So we want to call these now something consistent. Instead of always saying a linear approximation, a quadratic approximation, it just cubic approximation, the names get a little bit choppy. So let's call them instead a polynomial of degree 1, a polynomial of degree 2, a polynomial, or even they use the word order as well. Polynomial order 1, order 2, the first order. Okay, any Star Wars fans here? First order? No? Okay. So you've got first order, second order, third order. So let's remember how we did that. When we built the linearization, you start with f of 2. So I've got that over there. F of 2 is 0. And then plus f prime of 2, which was 1. Okay, Juliet, can you do the quadratic one? It's still going to start with 0.
Yeah, 0.
And still has 1. Okay, and now we're going to add on to that.
Is it 1/2? And then, is it x to the, or 1 over x minus 1?
Let's see. No, we're using the actual numerical value.
Oh.
Yeah, we need the value.
Then the 1.
I think I wrote positive 1 for the second derivative, right? We need our second derivative value.
Oh, okay.
Negative 1 is our second derivative value. Okay, and then what about the x minus 2 term? That would be squared, wouldn't it? Because we're adding on the square. Okay, so this was our lesson last week that we're building on. All right. So Rain, can you tackle maybe the cubic? Let's try that. Okay, so 0, and then 1, and then plus this 1. Okay, then let's add on a cubic term.
1/3
Okay,
times 2 x minus 2 to the 4th.
to the, Oh, whoops, I did it wrong. This is not supposed to be a 2. That's the 2. There's our 3. Okay, good. Now, I can totally understand why you thought it was 1/3. But let me clarify that it's not. Okay, it's not just 1/3. What Taylor developed in here is these are actually factorials. You just couldn't tell that they were factorials when we got up to here, because what's the value of 2 factorial? 2. What's the value of 1 factorial? 1. What's the value of 0 factorial? Also 1. So you couldn't tell that they were factorials because it had been nothing different than the number it was, but it's actually 3 factorial. So instead of being 1/3, it's going to be 1/6. All right, so we're clarifying that now, that this is the fraction of 1/6. Okay, so this would be called your polynomial of order 3, or you could call it a cubic approximation, which is centered at 2, and we're getting increasingly more accurate. Okay, so remember, a linearization has a common point with a common what? Slope, right. Linearization, common point, common slope. Quadratic, common point, common slope, common concavity. Okay, the third, the cubic, common point, common slope, common concavity, common, do you remember what we call the triple one? Jerk. Okay, common jerk. So every time we extend our order a little farther, the polynomial more closely matches properties of the original function. So it's got the same type of slope, it has the same type of concavity, it's going to have the same type of change in concavity, which we call jerk. Each time we're getting, so in those blanks there, we're getting increasingly accurate along an increasingly wider interval. In other words, the accuracy stays valid longer. We saw that on Friday when we drew those pictures. A tangent line does not stay accurate very long. It's a very small section where a tangent line would match. If you match concavity, now it's gonna, that similarity is gonna extend to a wider interval. If you add cubic, it's gonna extend farther. The higher the polynomial order, the more accuracy along an increasingly wider interval. All right, so this is so intimidating when people walk in and look at this. Okay, it looks to them like this is just crazy madness here, but all of this should make sense to us. We are going to build a Taylor polynomial. What does this symbol mean we're doing?
Summation.
Means we're adding things, okay? So we're going to build a Taylor polynomial. We're going to add as we go. And what are we adding? Well, this part, this little k right here, just means that you're changing the derivative. So it would be f to the 1 prime, f to the 2 primes, f to the 3 primes. We're changing as we go. We're dividing by the factorial of that same value. We're centering it around the term that is convenient to us to center. And then we're raising the power to that same, so k shows up here. You could call it n if you wanted as well. But so we've got, that's how we're building these Taylor polynomials. It's an addition, building particular terms out. The longer you go, the more accuracy you have. Okay, so where that would be intimidating to a lot of people to walk in and look at all that Greek, and we've got exclamation points, all kinds of stuff going on there, but we understand what all of that means. All right, so next slide. So this is what it looks like when you start to build it out. So that top part's the same. You start with your f of a. That's like your plus c value. It's the initial condition. That's what we've called it in the past. The initial condition is here. That is what the f value is. Then you're going to make sure that it shares the slope. So you move on, and I would like you to maybe add that this is divided by 1 factorial, just like the other ones are divided by 2 factorial and 3 factorial and n factorial all the way. In fact, your initial condition is divided by 0 factorial as well. It's just that 0 factorial, whoops, happens to be 1. So that's divided by 0 factorial. And then we're sharing the common concavity by introducing the second derivative. So we divide that by 2 factorial. Okay, any questions so far? These are fun to make. All right, well, let's try it. Let's try making a fourth order Taylor polynomial to approximate cosine around 0 as our focus point. So we all know what cosine looks like. Cosine waves like this. Can we create a fourth order polynomial that would also approximate that? So let me just, what we're going to do, okay, so here's a sinusoidal wave, right, which goes on forever. Around 0, and 0 on cosine is going to be about right here, above the x-axis. Around there, create a fourth order polynomial. So a fourth order is a W shape, right? You know what parabolas look like, you know what cubics look like, a fourth order polynomial. So we're going to create a fourth order polynomial that's going to share that point, share the concavity, share the eventual jerk, share fourth order properties. So it's going to come up and it's going to look like this. And it's going to look like this, it's going to look like that, and then it's going to stop matching. Okay, so we're going to create this polynomial here, which will match cosine around that point throughout this. Okay, that's what that's going to look like. All right, so let's try it. In terms of just keeping things straight, I usually work across in my like derivatives. This is kind of how I go when I build it. I'm going to start, okay, I know I've got cos 2x. That'll be my first thing. Then I work on my next derivative. My next derivative is going to be negative 2 sine 2x. That's derivative number 1. Derivative number 2, negative 4 cos 2x. Derivative number 3, I'll need positive 8 sine 2x. And derivative number 4 will be 16 cos 2x. So I just kind of work across. And then for my own purposes, I usually then drop 0 in just to help keep me straight. So when I drop 0 into cosine 2x, I get 1. When I drop 0 into negative 2 sine 2x, I get 0. When I drop 0 into the next one, I'm going to get negative 4. And then I drop and I get 0 again, and then I'm going to get 16. So those are my values. So just remember each of these, this is what f of 0 is. This is what f prime of 0 is. This is f double prime of 0, f triple prime of 0, and f fourth derivative of 0. So those are my values I'll be using. Those are called the coefficients. So then we're ready to build our Taylor polynomial. So you say, all right, P4 of x. I am building a fourth degree Taylor polynomial. All right, so we'll each take a turn. Juliet, you can start. What's the first part going to be? 1. Thank you. All right, Alex, what's the next part going to be when I add to it?
Negative sine 2x x.
Okay, you're close. I don't want to use, yes, I'm going to use this derivative, but I want to use the numerical value that comes from when I plug 0 in.
0.
Okay, that's going to be 0. Okay, I gave you a nice easy one. All right, Kaylin, how about the next one? Plus. So we're going to use our second derivative now, which turned out to be
negative
4.
4.
We're going to divide that by,
Was this the second?
mm-hmm, it's the second one,
2.
2 or 2 factorial, and then,
X minus a squared.
and where am I centering this?
0.
Okay, so x minus 0 squared, which will be x squared. All right, Edson, the third piece of our Taylor polynomial.
0.
0. Okay, done. All right, Christian, finish it up.
1 over 24.
Is it, okay, let's not reduce it yet. Let's see it in its, we'll clean it up in just a minute.
16 over 4 factorial.
Okay, and 4 factorial is?
24.
Okay, good.
And times x minus 0 4.
All right, so 24 being 4 factorial, that's 1 times 2 times 3 times 4. So we can write it as 4 factorial while we're thinking about it. And then we would just want to clean that up. So this will be 1, and then we don't need the 0 term, and then we'll divide negative 4 by 2, so that'll be minus 2x squared. And then since 4 factorial is 24, what do you get when you reduce that? 2/3. So plus 2/3 x to the 4th. So this turned out actually to be a positive quartic. So could I create a positive quartic? I wish I got another color. Hang on. So my positive quartic, this would be a negative quartic. A positive one would come down here and then pick it up right there. There's a positive quartic that shares the same properties. And that would be the equation that we just came up with. 2/3 x to the 4th minus 2x squared plus 1. In other words, so if you overlaid cosine 2x graph, and that polynomial graph, they would overlay each other, centered at 0, for a certain interval. And if we made another higher order, they would overlay for a wider interval. Okay, is that making sense? Okay, pulling all the pieces together. Okay, let's try and build another one. Okay, let's try to find a polynomial that's going to model e to the x, and we're going to center it at 1, but I did not tell you what order to do. So what that means is you need to do enough of them till you find the pattern, and then you need to end me with a general term. Okay, so we're going to do enough to where we find a pattern, and we will end at the general term. Okay, well, I gave you a nice one to start with because we know that f of x is e to the x, and then f prime will also be e to the x, and f double prime will also be e to the x. So I've given you one that's very predictable. And so their values, when we plug in x equals 1 to center, it's going to be e, 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 all the way out. No matter what, the f to the k derivative will still be e to the k, or excuse me, will still be e to the x, and when x is 1, it will, no matter what, always be e. So then let's start building our polynomial, and I did not tell you what order, so we're going to build it, and then we'll see if we can generalize it to a general term. So this is going to be p sub n of x, where we're not specifying the order. All right, Rain, can you get us started? E. Okay, Edson, pick it up.
E times x minus 1.
And then over
Over
1. Okay, all right, Kaylin, pick it up from there.
E over 2 times x minus 1 squared.
Okay, Alex.
E to the 6 x minus e over 6
Mm-hmm.
x minus 1 to 3.
To the 3rd. Good. All right. Is anybody ready to try a general term? We could try another one. We can do another actual one. Juliet, give me another one.
E over 24
Mm-hmm.
to the x plus times x plus minus 1 to the 4th.
Okay. Anybody ready for a general term yet? Edson, you want to try?
Sure.
Okay. So plus dot 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 plus general term going to be
E over k or
n factorial.
times x minus 1 n.
Very good. Okay, and you just built a Taylor polynomial, and that is the general term for any term that would represent any term in that infinite polynomial. Okay, nice work. Okay, 7th. Okay, 7th order polynomial for sine centered at 0. And we're going to do a little calculation at the end with our calculators to see how close this actually is. All right, so I need 7 orders. So that starts me with sine x cos x, negative sine x, negative cos x, and then we repeat. All right, so those are first order all the way through all my needed derivatives. Okay, and then we're going to plug, yeah.
Just a quick question, is that first term considered term 1 or term 0?
Okay, so it is like a zeroth term, term 0. So we actually end up with eight terms. But if you figure you're going backwards, this is like 7, 6, 5, 4, because I'm counting derivatives, right? 3, 2, first derivative, and then the initial condition. So the first one is the initial condition, and then derivatives 1, 2, 3, 4, 5, 6, 7 to create it, okay? All right, so we're going to start. Rain, why don't you give us, what does our initial condition turn out to be?
0.
Okay, so 0, and then go, want to just keep going? What's the next one?
1,
1,
0,
uh-huh,
negative 1,
Uh-huh.
0,
Uh-huh.
1, 0, negative 1.
okay, great. So our seventh order, even though it sounded like, oh, 7, I only really have half the terms because a bunch of the terms are 0 and they wipe out. All right, so we want P7 of x. Okay, all right, so Christian, let's start building that, and then you can just call who you're passing off to.
0.
Okay, let's skip the 0 terms. Is that okay? Let's do the non-zero terms. How about? Okay.
1 times x minus 1.
Okay, so where's it centered? Okay, so it's centered at 0, so I can just say 1 over 1 factorial times x to the first. Okay, pass it off. Juliet, okay?
Skipping the 0.
Yeah, we're skipping the 0.
So then it would be 1 6 times negative 1. So negative 1 6.
Okay.
And then times x to the third.
Okay, good. Passing 2.
Okay.
Okay,
And it would be 1 times, or 1 over, whatever 4 factorial. No, next one.
5 factorial. Uh-huh.
What is it?
That would be helpful.
24 times 5.
Uh-huh. 120.
100.
120. Yeah, 25. Yeah, 120. So it's helpful to kind of know some of the first factorials. So 120 is going to be 5 factorial. Okay, and then the rest of the term.
X to the x.
Okay, good. All right, one last pass. Passing 2.
Caitlin.
All right, Kaylin.
The negative 1 over 7 factorial, the x to the 7.
Okay,
Um,
yeah, 7 factorial. So 720 is 6 factorial. And then 7 factorial is 50, 40. Okay, so you just created a polynomial that we're saying is going to very closely approximate sine of 1, 0.1, excuse me. All right, so in radian mode, let's compare, since we do have the luxury of having our calculators, let's let's check what sine of 0.1 is, and let's compare it to how accurate this polynomial is, and let's see how these guys back in the 16 and 1700s were doing on their accuracy. Okay, so I am curious what P7 of 0.1 is compared to sine of 0.1. Edson, you got one of them? Which one were you working on?
Sine of 0.1
Okay.
is
0.998. Okay. Anybody got the polynomial? We're plugging in 0.1 into our nice little 7th degree polynomial. Did you get it yet, Alex? Or are you working on it? Oh, he's writing.
It comes out to be identical to as many digits as the calculator will show.
As many, so how many, what do we get? Like 9?
9, 8, and then they both have also 3, 3, 4, 1, 6, 6.
4166. And the other one's exact. So a perfect match to 9, 10 decimal places, okay, that these guys were coming up with without the benefit of a calculator. Okay? So not too shabby. Pretty impressive that they could do that. Okay, this was the same question we launched our day with on Would You Rather. This is the question. Here's the third order polynomial, asking you to center it at 1. Well, could you plug 1 into this polynomial?
Yeah.
Sure, no problem. But would you want to plug in, like we did earlier, 0.9 or 0.95 or 1.02? Okay, then it's a lot harder to plug it into a polynomial. So that's the argument. Why would we bother constructing a new polynomial to approximate a function that's already a polynomial? It's because it makes the math easier if you center it somewhere else. So we actually did this question already. It was in our warm-up earlier, so we can skip this one. And here's the rationale on there, right? This is exactly what we did. What would you rather use? Okay, would you rather? All right, sometimes all you're given, like on an AP problem, is a table like this. Because it'll be like multiple choice question. And they don't want you to waste your time doing derivatives. They're just going to give you this, and they just want to see, can you build it? Okay, so that's why I was showing you that's how we're going to set that up. So this one has 5 derivatives, and we want to create it centered at the number 2. All right, so we'll do the same thing. All right, Edson, you can get us started. We want a P4. Starts with what?
I'm not sure. Is it just 2?
Okay. Oh, this should have, my fault. That should be a F.
Okay.
Sorry.
So 2.
Thanks. It starts with 2, my fault. Yep, you're right. There wasn't a Y value the way I typed it. All right, passing 2.
Alex.
Alex, pass to you.
Ooh, 5 over 2. Derivative.
Okay, so 5 over
1.
5 over 1. Okay, then what?
Derivative of
We have the derivative of fx. That's 5.
x minus.
Okay, there we go. X minus 2. All right, so that would be a linearization. Okay, who are you passing to, Alex? Okay, Christian? Yeah, Christian. Okay.
Plus 7 over 2 times x minus 2 squared,
Okay, passing.
right?
Plus 11 over 3 factorial, which is 11 over 6, times x minus 2, so like third.
Okay. Passing.
Julia.
Okay.
15 over 24 times x minus 2 over 4.
Good. Okay, great. What kind of numbers would make sense to plug in here if we were going to use it to approximate?
2.1.
2.1,
1.9.
1.9. Okay. Would it be reasonable to go as far as like 2.4? Okay, it's a fourth degree, so if we wanted, we were given the 5, the 5th derivative, so if we wanted more accuracy, if we want to widen our interval, we would go for more accuracy. Okay, it doesn't take a very high order to get enough accuracy where you're above, like, where would the threshold be, right? If you were doing 2.4, you'd want it to be centered around 2, but what if you were doing 2.5? Would you center it around 2 or would you center it around 3? Maybe try both and see, compare the two, okay? Because it's right in the middle. All right.